It's talking about reducing costs in building and data set using deep and active learning. Please, very welcome to Filipa Castro to the stage. Filipa Castro holds a Master in Biomedical Engineering at the Faculty of Engineering of University of Porto. During her study, she worked as an intern in insect technology, where she developed an eye-tracked bite system for obtaining gas and math for radiologists. As her interest in computer vision and artificial intelligence start to grow, she decided to do her master thesis in the Delphi University of Technology, where she built a data set and an action recognition system for sport. She's currently a computer vision and machine learning researcher at Abyssal, working on image and video recognition with the ambitious goal of automating subsea operations. Thank you very much.
Thank you.
Filipa.
Thanks for the invitation to be here today. My name is Filipa Castro. I'm an AI researcher at Abyssal. And today I would like to firstly give you some context about the work we have been doing at Abyssal as a software company for the subsea, to then go deeper in our latest research work in artificial intelligence. So please let me start by showing you an overview of our most recent technologies.
The digital twin is a virtual model representation that allows data analysis and system monitoring to streamline operations and generate actionable intelligence. By pairing the physical and virtual world, the Abyssal platform integrates an ecosystem of applications. It combines data and intelligence to represent the structure, context, and behavior of its physical counterpart. All Abyssal applications are connected through a cloud infrastructure that reads and integrates relevant data such as imagery, 3D models, survey information, and documentation from third-party systems. All data is kept securely in the Abyssal cloud and is accessible to all platform applications. The Abyssal Designer provides engineers with an enhanced 3D digital view, accurate GIS positioning, and contextualized data of the subsea environment. Teams can collaborate in the 3D field layout design, perform accurate feasibility studies, and reliable risk assessments. All data generated in the Designer is securely synchronized and correlated with the digital twin. The asset geometry data, physical and environmental properties available in the platform allow the creation of realistic simulations. The Abyssal Simulator is a 3D rendering engine with accurate physics simulation models. Virtual scenarios are driven by integrating real-world information. Engineers can perform virtual system integration testing while planning procedures, assessing the feasibility of subsea tooling tasks, performing accessibility and maneuverability studies, executing constructability reviews, and identifying opportunities for increased efficiency. Operation planning teams no longer need to execute these tasks on the field, drastically reducing cost, time, and risk. All data generated in the simulator is synchronized and correlated in the cloud infrastructure, further enriching the digital twin with created procedures, planned operations, simulation results, and simulation videos. The digital twin data also enhances real-time operations. The Abyssal Offshore is a real-time monitoring, navigation, and management tool for offshore operations. Based on 3D visualization, GIS, and augmented reality technology, it provides operators with a live 3D overview of the operations environment, increasing their overall visibility and spatial awareness. The real-time visualization of the 3D environment, coupled with the augmented reality feature, improves safety and efficiency in navigation and eliminates any downtime due to low visibility. The ability to create virtual flight paths and virtual safety areas enhances real-time communication and collaboration, reducing risk and response times. the capability to connect to any asset integrity management system and enable the visualization of historical data and performance metrics of subsea assets improves both safety and reliability. Additional features like the advanced video recording system, digital dive logs, and instant reports allows engineers, pilots, and supervisors to focus their time on value-added tasks. The live connection to the platform enables the correlation of real-time telemetry, video, and dive logs. Abyssal Command Center provides onshore personnel with a real-time 3D overview of the entire operations environment through the use of cloud and satellite communication technologies, increasing their overall knowledge of the operation and allowing them to act either in emergency response or in routine situations. The cloud infrastructure offers fully web-based functionality to any compatible browser, providing Abyssal's engineering and operational applications to anyone, anytime, anywhere. Abyssal, vision in depth.
So you can imagine that when working with all of this technology for the subsea, you are in the right position to be more ambitious and to step forward to add some intelligence to this system. And that's what we are currently doing in our research team. We have two main objectives. So the first one is to reconstruct automatically the 3D scene that is surrounding the ROV. And the second objective is to extract knowledge from this ROV video to detect, for instance, subsea entities or threats to these entities. And by combining these two, we can then map these regions of interest in the extracted point cloud. And we have a complete knowledge of the 3D scene. The ROV can understand and perceive what surrounds him, and then it can start to take its own decisions. It can start to operate autonomously. So the work I'm presenting today is more focused on this task. Our goal is to automatically detect subsea entities or integrity threats, anomalies. So basic example here. Here our entity of interest is simply a fish. And it's simple as that. We want an automatic way of telling us, given a group of frames, these frames don't have fish, this frame has a fish, in a fast way, automatic way. And so we are using machine learning for this. As you may know, machine learning learns with a lot of examples. So we have this training phase where we extract frames from the training videos, and we start to learn which patterns correspond to a fish, which patterns correspond to a frame that has no fish. And step by step, a new model is born that is capable of detecting fish in ROV videos. And then, of course, we want to apply this model to new videos that were never seen before. We extract frames exactly the same way. We run the model, and then the output is exactly the same frames, but with the label. It has fish or it has no fish. Deep learning, in particular, a subset of machine learning, uses convolutional neural networks to train this model. And the problem of deep learning, even though it achieves human level performance, the problem is that it requires huge amounts of labeled data. And by labeled data, I mean that you have to give him not only the frames, but a corresponding label that tells there is a fish. So you need experts, and biologists do this all the time, manually labeling these frames and telling, here I see a fish, here I don't see a fish. And what is the common process when you want to build these data sets for the subsea? You simply random sample from your unlabeled data set, you give frames to experts, and sample by sample, you start to build your labeled data set. Sample by sample, also you start to feel the pain of such a time-consuming, repetitive, and very expensive task. So thankfully, there is active learning. And active learning is based on the idea that you can minimize the cost and the effort of labeling this data if you let that the model suggest you which are the most relevant frames that we should label next. And because we are convinced that active learning works, I'm presenting our framework where we include deep and active learning. Firstly, we have here a difference. We don't give experts frames, isolated frames. We give instead video segments. This is our unity to build a data set, just because it's easier and more efficient for a biologist to annotate continuous frames, a video segment instead of isolated frames. And we start by using random sampling, because at the beginning we have no label data at all to train a model. So you use random sampling because it's automatic, completely unbiased. And we build our first very, very small data set. Once we have label data, we can train our first model and we can start to apply active learning. So we would like that our model will look at all these frames that are unlabeled and tell, okay, which ones are the best to annotate next. But because there are a lot of them, it will take a lot of time to run on all these segments. So we propose to use random sampling and select just a subset of these segments. And now our model will run in these segments. And its job is basically to rank all the segments and then tell which are the K top segments that are most relevant and that we should annotate next. This is an iterative process. So the model is always trained on the most recent data set, so that the most recent examples that have been just added are taken into account to the next decision. Now I would like to focus more on this part of the ranking to explain you how do we do that. So we have a list of segments. We want to order them in terms of relevance. How do we do this? Basically starting by assigning a score not to the segment but to the frames of this segment. And we extract the frames and we run this model on the frames, basically to get an opinion of this model. The model will output a value between 0 and 1. 0 if it's very sure that there are no fish, and 1 if around 1 if it's sure that there are fish there, and around 0.5 if it's still unsure of what to do. So what is the best? How should I rank these frames according to this opinion that the model gave me? It depends on what you consider to be the most relevant. So if you think that the most relevant frames are the ones in which the model is more unsure about, so you can imagine that if the model is more unsure about this, it will be good to add these samples to the next step, because then you will learn the samples that you was unsure about. But also you can think that maybe it's better to add positive samples. Maybe it's better that he sees a lot of fish to understand the difference between the fish. And then you will use uncertainty sampling if you want to assign a higher score to the frames that are more uncertain. And you will use positive sampling if you want to assign a higher score to the frames that contain fish. After having a score for each frame, we can aggregate them to have a segment score. And you can either take the mean value of these frames or the maximum. This is quite simple. And the best way, the mean, the maximum, the positive, or the uncertain, we should make some experiments to tell us which is the best one. So we run this experiment with 50 trained segments, 60 validation, 50 for testing and for evaluation. And the oracle here represents the unlabeled segments. And the first experiment we ran was, of course, random sampling, because it's our competitor, let's say. So in the y-axis, you have the performance in terms of average precision, and in the x-axis, you have the active learning step. So in one step, I annotate, imagine 40 samples, segments, then more 40, 40, 40. So I'm annotating in this direction. And you can see that with random sampling, you spend like 7 steps annotating in a dummy way, because you don't gain anything in terms of performance. And what if we use active learning? These are the different combinations that we can use with the methods that I talked before. And you see that with active learning, you are sampling the most relevant frames from the beginning, so you are gaining in performance from the beginning. The best method is actually positive sampling, because with 50% of the data, you achieve almost top performance, so the plateau that you see here. So basically, we are taking this method to annotate our new data sets from now on. This is basically our framework that I presented before, and we have chosen now max positive sampling. These are some of the results we are getting in the subsea data sets. And positive ratio is a good metric. Why? Because in subsea data sets, it's very common that you have very unbalanced data. As you can imagine, we have tons of hours of video and just like 2% as fish. Or if you are trying to find an anomaly in a pipeline, you will see this anomaly not very often. So we want to control the positive ratio because we are using positive sampling, so trying to get the positive examples. And we see that at each iteration step, we can really increase this number of positive examples. We are getting more fish here. And you can see that this leads to an improvement in performance, actually, which is very common in machine learning, because once you balance your data set, the performance will be better. In terms of cost reduction, we did a small, an approximation, basically, of what we would spend with random sampling. And this is what we actually spent with our method, so we can reduce the costs by approximately 80%. And with less 80% of effort, we are getting results like this. This is the task of fish detection. And the red pixels, the hotter colors, represent the pixels in which the model is more confident there are fish. So you can see he is looking exactly in the places that we also see fish. So it's learning very well. I also imagine that you are not all interested in detecting fish. So I can tell you that we are using exactly the same methodologies and having the same results for detecting subsea structures, for detecting the ROV itself. Entities like sacrificial anodes that normally contain anomalies, biofouling labels or gauges, because then we can automatically read and get information from them, or even anomalies like the free span. I cannot actually show you all of the results of this. Hopefully you can visit us outside and see more, but this is the detection, like the yellow shows where the model is confident that there is an ROV. And you can imagine that it's very important that the ROV recognize its own arm, because then it can perceive where to move this arm autonomously. So, quick review. We came here today basically to show how we are using deep and active learning for the subsea and industry, and to build data sets with low costs. We basically label video segments instead of frames. We propose active learning to reduce the costs and smartly sample the segments to annotate. And we use positive sampling because it's a good strategy for this type of data sets. Our method was shown to reduce the costs by 80%. And the good news is that you can use it to deploy any recognition system for the subsea. I hope you have time to get to know more about our research outside in our stand. Thanks very much for your attention, and I'm now open to your questions.
Thank you very much, Filipa. We have time for questions. Any question? Okay, I have one question. Maybe very stupid question. So
There are no stupid questions.
You say the ROV has the possibility to not recognize his arm. Mm-hmm. So, but what happens if the ROV move a rock or a dust and can recognize that things as well as a nose of fish?
Yes, so if we are talking and if you are ambitioning to have an autonomous ROV, you will need to recognize everything that is around him. So it needs to recognize the arm, it needs to recognize the rock and everything. So that, and also, and that's why the reconstruction that I talked about and that you can get to know more outside, it's important that he understands the distance of each thing, the distance of the ROV, mm-hmm. And this has to do with the reconstruction part and with depth, estimation of depth. And yes, it's absolutely essential that he knows and recognizes everything and the distance of the things. Yeah.
Okay. Okay. Thank you very much.
Thanks.
Thank you very much for your presentation. Very nice presentation.
Obrigada.
Okay.